for making you to strain yourselves at the very end of the session, because I will be talking about relatively new phenomena that I never saw discussed before. So perhaps you will need to pay some attention to what I'm saying. It might be interesting. And this is all about statistical properties of atomic calculations. Particularly, I will be speaking about calculations of transition rates. But yeah, I understand that it's maybe not directly related to what most of you are doing. But we already heard several times that collision rates are proportional to oscillator strength. So it might be relevant, and I'm sure that some of these things I will be showing you is also appearing in the cross-sections calculations. All right, so how am I attempting to estimate uncertainties of a calculation? First of all, a calculation is not about calculating just one value. Typically, in plasma modeling, you need hundreds or maybe millions of data, and your atomic code can spit it out in one shot. And then you have to evaluate uncertainty for every value that you got from the code, not just for one transition or one cross-section or one rate coefficient at a time, but for all of them. So I'm trying to present a method to at least partially do this for the whole bunch of your output data. And how to do that? I am attempting to assess it by varying parameters of the atomic code. What do I mean by parameters? Every atomic code has some built-in parameters. And I'm not talking about grid dimensions or something numerical. I am talking about physical things. Most famous of these parameters are the Slater parameters. When people understood that unless you can calculate these Slater integrals analytically and sort of, then they're not parameters in this sense, because they are ab initio values. You got them from initial principles, and that's what you get. But if you try to adjust them in certain ways, then the precision of your calculated data improves drastically. And you can adjust them by knowing a little bit of experimental data. You can adjust these parameters so that the rest of your generated data predicts the unknown quantities with accuracy much better than is possible with even the huge sophisticated atomic codes ab initio. So this is what I will be doing. I will be varying these Slater parameters, and also there is another kind of parameters affecting the rates. This is transition moments, multipole moments, which I also treat as input parameters. This method, in principle, can work with any atomic code if you do some coding. Most of the codes would need some programming changes in them, because there are no methods available for users to manipulate these parameters that are actually present in the code. It saves them somewhere on disk and then reuses it, but never gives it to you to manipulate. But there are a few codes that can do that, and one of them is Cowan's code, which I work with very much, and there are a few others also. So because I did that with Cowan code, I need to tell you a little bit how the code works, so that you would see what was going on. It's simpler for me to use the pointer. So the code consists in several parts. The first part of the code computes single configuration parameters such as average energies and Slater parameters for each configuration. And also it gives you transition matrix elements, dipole or magnetic dipole or quadrupole matrix elements. And then the next code takes these parameters as input and builds the Hamiltonian matrix, diagonalizes it, and spits out the eigenvalues, eigenvectors, transition wavelengths, line strengths, and also, which is very important, a matrix of derivatives of the Slater parameters over the eigenenergies. Then the next code, the final one, which is used for this least squares adjustment procedure, it reads in all this information from the previous code, especially the parameter values and eigenvalues and eigenvectors, and this matrix of derivatives. And you combine this with experimental values for known for some of the energy levels, and you make it vary the parameters iteratively so that it produces the best fit to these known energy levels. All you need to do for this iterative procedure is this matrix of derivatives. Then a very simple Newton method allows you iteratively change the parameter values, knowing the direction in which each of them has to change on each iteration from these residuals from experiment. And as a result, you obtain a very good approximation of your energies, and many people saw that in addition to that, the transition rates also improved dramatically. And what is significant is that you know these final values of parameters with a finite and well-defined accuracy. You just combine these residuals in quadrature, and this is your uncertainty in the parameter values. So the idea of the method was that now, well, I have this good calculation and transition rates generated with this with these fitted values of parameters. What if I try to randomly vary these parameters around the fitted values within these limits that I got from the fitting, and compare the rates that I obtain after each of these trials? This will give me some handle on the behavior of statistics of my results. So this is what I will be showing you. In principle, this ideology is in line with all traditional methods that we know. Most of the methods of assessing uncertainties rely on comparison of results obtained with one method with another method. And also there are other comparisons within the method itself, like you can compare length and velocity forms, and you can investigate convergence of your method when you extend the basis set. These are internal methods. So this method I'm talking about, it's also internal. But you do it with the same basis set. You only slightly vary the parameters involved. I will not be talking much about that. The only thing that matters for transition rates is that there is one feature that many people observed. Weak transitions are usually calculated worse than strong transitions. And the meaning of strong and weak has to be expressed in terms of the line strength. not the oscillator strength, not the A value, because these are the secondary quantities derived from your line strength, which is the reduced multipole moment squared. Nevertheless, the line strength depends only weakly on transition energy, but these factors like transition rate or oscillator strength, they strongly depend on transition energy. And this changes the meaning of your strong and weak, maybe by several orders of magnitude. And the comparison becomes not very clear. All right. So this is how the typical traditional comparison would look. This strong transition, you compare one calculation with another. Each point is a difference between two calculations for one transition. So as many points, as many transitions there are. Some strong, some weak. And typically you see for strong transitions good agreement between different methods. And it rapidly becomes worse when you go to weaker transitions. Now, the test bed for this method was chosen to be titanium-like iron, which has 34 levels in the ground configuration. And I was calculating magnetic dipole and electric quadrupole transitions within the ground state, within the ground configuration. This was chosen because I already had a very good fitting for this system. And also because these levels are not mixing very much with highly excited ones. And when you change your values of parameters, there is very little risk that you can make a mistake identifying the levels you got from different calculations with each other. So they do not shift too much, and the order does not change. It's very easy from this technical point of view. And there are about 600 transitions possible in this configuration. Of course, on top of that, there were some interacting configurations added. So in total, there were like 38 electric quadrupole transition matrix elements, and there were 86 Slater parameters and 61 CI parameters. The Slater parameters are average energy, some electrostatic integrals, and some effective parameters describing configuration interactions not included explicitly in the model, like core correlations and core valence. There are certain methods that allow you to effectively account for them by including these adjustable parameters. In fact, the number of varying parameters was less than that because many of them were linked together at fixed ratios, but still there were like about 50 parameters that I was changing randomly. So I started with varying only these E2 transition matrix elements, arbitrarily choosing the limit for this variation at 1%. Nobody knows what is the accuracy actually. Some people argue that it may be 20%, but I wanted to see the sensitivity, how different transitions behave at this very small variation of this crucial parameter for electric quadrupole transitions. And the next step would be to vary all the Slater parameters around each of them around its different error bar. Then each calculation in principle produces a different set of eigenvalues and eigenvectors, and you have to build a correspondence between them to keep trace of identities. it is a non-trivial problem in general, but in this particular case, as I said, it was rather simple to do. So this plot sort of resembles the previous comparison, but it's qualitatively different. In the previous plot with these scattered points, each point was a difference between two calculations, and it was going both positive direction and negative, of course. Here, what I'm showing is the root mean square deviation, or a measure of uncertainty in the results. Each point, again, is one transition. But now it's an RMS deviation over 400 calculations in this case. And of course, all these values are positive. So I was expecting to see some smooth curve. Not expecting, but hoping. Like, we know that strong transitions are better, weak transitions are worse, so there should be some dependence. Well, nature may be beautiful and simple, but our methods of studying it are ugly and cumbersome. So this is what we got. Every transition has its own sensitivity to this 1% variation, as I said. This is only for E2 transitions, of course, because M1 transitions do not have any such parameter involved. In general, yes, there is a tendency that strong transitions are better than weak ones, but even within a range of close line strengths, you see some transitions that differ from others by a factor of 10 in their sensitivity, or even for weak transitions. Some of them can be bad, and some of them can be still good. So you really need to know to assess the quality of each transition separately. There is no way to tell exactly which one of them will be sensitive or not before doing something. Maybe something like that, maybe something else. Okay, so let's now move on. Now we turn on varying all the parameters, including the Slater parameters. So now we have variations not only for E2 parameters, but also for M1. Let's look just at the top portion of this. And we see common behavior, basically, although there are some details, like there are steps in that, but they are not distinct, but somewhat with a great scatter around. And we see the same thing, that there is variation. Some magnetic dipole transitions, the strongest ones, are really insensitive to these small changes in the parameters. But some are really bad. This is percentages. So you see it's 1,000% variation. And again, some medium strength transitions are clustered around 10% accuracy, but some of them are 10 times worse. And I think this graph was built with statistics of 1,000 trials. And I thought, why 1,000? Because usually when we do this error assessment, we compare 2, maybe 3, if we are lucky, 5 different calculations with each other and hope we're getting a right result. Right? So I thought, well, 1,000 is more than enough. I will surely get the right answer from this. I was naive, as we will see. Anyway, the empty circles are shown here to, I was trying to trace the influence of cancellation effects. So many people were talking about, well, if there are a few data points that are unreasonably far from expectations, everybody blames it on cancellations. So I was trying to confirm that this is really the culprit. Like these extremely uncertainly calculated guys are really those affected by cancellations. The empty circles are transitions affected by cancellation effects. But you can see that even some of these transitions affected by cancellation are still calculated very well, and vice versa. Some transitions that have negligible cancellation, they have large uncertainties, like especially these transitions here, 100% uncertainty. So the bottom part was designed to look at it at a more systematic way, but the basic conclusion was that no, cancellation cannot be identified as the ultimate culprit. And basically the reason for that is that the cancellation happens when your transition rate is calculated as a small difference between two large quantities, right? So if both of these quantities, the positive and negative part, are calculated extremely precisely and are insensitive to your uncertainties in the parameters, then still, despite you have the cancellation, but the result is still very accurate and it remains stable. So it happens, not always, but yes, it happens. Now let's look at what the distributions of results look for individual transitions. The plots are just number of trials, trial 1 to 1,000, and then how the result deviates from the nominal value obtained with initial fitting. So you see that there is a great scatter in the results. These are three transitions. These slides are one transition, this is another one, and this is a third one. For some transitions, you see some extreme deviates on one side, and for another transition, they are on another side. And generally, the distributions do not look symmetrical. You don't have them evenly distributed for deviations on one side or another side. My first idea was that I can make them symmetrical using some function of transition rate instead of the rate itself. Say, looking at the distribution of a to power 1/3 or at a logarithm. Well, I got some transitions improved by one transformation, other by another transformation, but some could not be improved by any of these. Why I was even looking for this symmetrization? Because when you have such strongly asymmetrical distributions with a high number of extreme outliers, you cannot really speak about uncertainty in a numerical, statistically sound way. Because if you will try to define, you calculate one value, and you try to define the probability that the true value lies within, say, 95% probability within plus A and minus B interval from this. You cannot get it with such distributions. You need normal distribution for that. And so that's why statisticians devised elaborate methods of how to rectify such distributions to make them more close to normal. There exists a very nice function for that, which is actually a combination of power and logarithm law. And despite its piecewise character, it's a continuous function. So finally, I found out that I can use this universal transformation and vary the parameter p for each transition separately and find the best way to make the distribution for each transition close to normal, with few exceptions. There are several ways of building such best transformations, but the most proficient ones are based on so-called normal probability plots. If you plot your data in a certain way against the size of the deviation from the mean, this is one deviation, 2, 3, 4, and this is negative side. The data should organize themselves linearly if they are normally distributed. So if you choose the transformation properly, you can rectify the originally distorted distributions, make them normal, or almost normal. You can do that using strictly defined procedures, like finding the maximum of the correlation coefficient of this normal probability plot, or another method is to minimize the skewness, or find the point where the distribution is symmetrical. It is not universal, but in this case it did work the same way. Now, what I got for this optimal parameter, this is a distribution of a number of transitions. If you remember, there were 600 transitions. I got some maximum around 1/3 and another on the negative side, and basically a very broad, small pedestal with wide range of these parameters. Now, just for out of curiosity, I decided to make a trial with, make a run with 10,000 trials instead of 1,000, and I got a little bit different. This peak basically disappeared, and it became wider. I didn't even show, but there are values of p for some transition around 2,000. So you see how grossly asymmetric the distributions were, that I had to apply power of 2,000 in order to make them symmetrical. And why the change between 1,000 and 10,000? This is because all statistical properties that you derive from statistics strongly depend on these extreme outliers. And when you have small statistics, there is little chance that you will see enough of them to make correct conclusions, not only about the shape of the distribution, but also about the RMS deviation, or uncertainty value as we usually define it. So you make mistakes when you have a little number of comparisons, small number. You make big mistakes in determining your uncertainty based on statistics. So when I yes, I made some investigation. If I require that the standard deviation must be known accurately, with accuracy better than 20%, then if you compare just 10 data sets with each other, in 99% you get a wrong result. You actually have to go to 1,000 or maybe 10,000 comparisons to do that. Only if you relax your requirement to know, say, a reasonable factor of 2 accuracy for your standard deviation, then 10 data sets get you 90% of results correct in this sense. So just a brief reminder that this is not a complete investigation of uncertainties, but only one part of internal properties of the model I was using. To have a complete understanding of your uncertainties of your atomic calculation, you also have to investigate other things like convergence trends and look at the length and velocity form comparison, for example, whatever means possible, and investigate possible contribution of neglected effects. Say Cowan code does not include spin, other orbit corrections, and so on. Does it matter? I have no idea for this particular problem. And also, there are external uncertainties, uncertainty estimates that you can get from comparison with other calculations, possibly more precise than yours. Okay. So the point was not to make a complete study. There are many things that I left undone, not done, I mean, for future research maybe. And there are problems in how to do that. How to estimate the uncertainty of those matrix elements, I have no idea. There was also an assumption that all these Slater parameters are independent of each other. Actually, they are correlated. There is a strong indication that this correlation is not too high, because if it was so, my Newton iterative method would not converge so fast, because in this method I estimate the direction and size of the change in each parameter from the levels. And if these estimates would contradict each other, I would never get to convergence. But they are correlated. There is some amount unknown to me. Unfortunately, there are only the derivatives that Cowan code gives you, but not the covariances. That would be desirable. I have an unconfirmed guess that these optimal transformations that I found may be reusable for other people who do it with other codes, because the matrices used to diagonalize in all atomic calculations are very similar. They may differ in size, but adding some small components to eigenvectors and these expansions when you calculate the line rates should not change the basic properties defined by the strong components already present in this calculation, except maybe for cases of strong cancellation, where adding small things may change the picture. There is one implication for plasma modeling. If you use the A values themselves as input, not generate them like Connor did in his modeling within the same model, but from external sources, and you try to vary them randomly to investigate the propagation of error, the distributions should not be symmetric. They should be skewed, and you should know how to do that, how to skew them properly. So I guess that's all. And this whole thing was published recently in the new journal ATAMP, where James Babb is the chief editor. So you can read more there. Why do I think that this requires a new field? Because I have a feeling that I did this research by brute force, by throwing dice, but a clever statistician should be able to devise mathematical methods of how the uncertainties of some parameters propagate through our matrix equations. I don't know how to do that, and very probably the methods do not exist now in statistics because it's still a developing field. This Box-Cox transformation that I was showing was invented only some 50 years ago. So it's a growing field too. But we need something combining our physics with their knowledge to do such investigations.
Okay, very short question. So your transformation, let's say Box-Cox and so on, I got feeling that it is valid only for small uncertainties, right or wrong?
Wrong. Short answer. I should say it is wrong for very few transitions, which in this case all happen to be extremely weak and insignificant. I can't say this is a rule, but some transitions have weird distribution functions that can't be rectified in this way.
We'll have a break. They come.